Imagine a tennis ball bouncing off a wall. Now imagine a tiny electron doing the same thing. Would you expect them to behave the same way? Welcome to the world of physics, where not everything is as it seems. In our quest to understand the universe, two fundamental theories have emerged. Classical mechanics, crafted by Isaac Newton, elegantly describes the motion of tangible objects like our bouncing tennis ball, moving at speeds much slower than light. It's a deterministic theory, where we can predict the future behavior of a system based on its initial conditions. But when we shrink down to the atomic and subatomic realms, classical mechanics falls short. Here, quantum mechanics takes the stage. Developed in the early 20th century, it introduces mind-bending concepts like wave-particle duality and uncertainty principle. It's a probabilistic theory, predicting only the likelihood of outcomes. So, on one hand, we have classical mechanics, a theory that works wonders with tennis balls and planets. On the other hand, we have quantum mechanics, which is a whole different ballgame. Rewind to the 17th century. Sir Isaac Newton, an English mathematician, lays the groundwork for classical mechanics. This was a time of profound scientific discovery, and at the heart of it all was Newton. He introduced concepts that are now fundamental in physics: mass, force, and acceleration. Mass is a measure of an object's resistance to change in motion, force is the push or pull on an object, and acceleration is the rate of change of velocity. Newton's laws of motion use these concepts to describe how objects move and interact. But what makes classical mechanics truly remarkable is its determinism. Given the initial conditions of a system such as the position and velocity of an object, Newton's laws allow us to predict precisely how that system will behave in the future. And thus, classical mechanics was born, giving us the tools to predict the motion of objects from a falling apple to orbiting planets. Fast forward to the early 20th century, a new theory emerges that turns our understanding of the universe on its head. This was the dawn of quantum mechanics, a radical departure from classical thinking. It introduced concepts that seemed to belong more in the realm of science fiction than science fact. The wave-particle duality, for instance, implies that particles like electrons and photons can behave as both particles and waves. The uncertainty principle, another cornerstone of quantum theory, tells us that it's impossible to simultaneously know both the position and momentum of a particle with absolute certainty. The most mind-bending concept, perhaps, is quantum superposition, which allows particles to exist in multiple states simultaneously until observed. Unlike the predictable world of classical mechanics, quantum mechanics is probabilistic. It doesn't tell us what will happen, but what could possibly happen. Quantum mechanics, the new kid on the block, introduces us to a world where particles can be in two places at once and cats can be both alive and dead. You might be wondering, how do these two theories differ exactly? Well, let's dive into the key distinctions. Classical mechanics, the brainchild of Isaac Newton, deals with the macroscopic world. Think planets, cars, or even a tiny speck of dust. It's deterministic in nature, which means, if you know the initial conditions of a system, you can precisely predict its future. It's like knowing the speed and direction of a baseball. You can tell where and when it will land. Now, enter quantum mechanics, a theory for the atomic and subatomic playground. It deals with particles so tiny that normal rules just don't apply. It's probabilistic, meaning we can only predict the likelihood of outcomes. Imagine throwing that baseball, but now it could land anywhere in the stadium with different probabilities. In the grand scheme of things, both classical mechanics and quantum mechanics have their own realms of success. One gives us a predictable universe, while the other gives us a universe full of probabilities.